started to talk to you guys about the nilpotent case, right? So let's talk more about that. Nilpotent maps. So essentially the point is this: you've got n is a mapping from say B to B, where we'll say the dimension of B is equal to, I don't know, k m, I suppose. It follows that I mean the definition of nilpotent in some sense demands that n to the m is equal to 0. And if you have n to some smaller number equal to 0, that means that there's a 0 eigenvector. And if there's a 0 eigenvector, that means that that means t is a factor of the characteristic polynomial. And then if you were to take the well, anyway, there's a way to argue this. I maybe can't say it, but anyway, it follows that n to the m is equal to 0, right? So, but you may actually have, of course, a it doesn't have to be that for a particular vector, you probably have some smaller power of n, which is non-zero, right? So as we talked about last time, for a given x, for x not equal to 0, there exists some k less than m, such that what? Such that n to the k acting on x is equal to 0, but n to the k minus 1 acting on x. I'm going to try not to. I mean, I'm thinking of n as being a matrix here, so if you'll forgive me for that. I guess I'm not being careful about matrix versus transformation in this discussion. So, I mean, maybe I should say n sub k of x, but I'm just not going to because there's too many of those. Well, fine. Yes, sir.
So is the n like the n sub beta beta, or like just
N is a nilpotent transformation.
Just
I
a
don't want to
transformation.
say what it is just now. It's just a nilpotent transformation.
Okay, so it's not.
Yeah. And so if we have this vector which is not equal to 0 and the k minus 1 power, we argued that what you could do is you could consider, say, alpha equal to the set. Let's see here. N sub k minus 1 acting on x, and so forth and so on, all the way down to nx and then x. And I claimed last time that you could show alpha is linearly independent, right? That was one of the claims that we have not shown yet. So I should probably prove that for you. We also argued. What did we argue? We argued that n times n sub k minus 1 of x is equal to what? Is equal to 0, right? So that implied that n sub k minus 1 of x is eigenvector, right? It's an eigenvector with eigenvalue lambda equals to 0. So the first thing in this set alpha is in fact an eigenvector with eigenvalue 0, right? And well, what would the second thing, by the way, be? And well, let me not get into that. More interesting thing to say. Okay, so that was one thing. And I also wanted to argue that so we'll let Cx equal to the span of alpha. Okay. We wanted to argue that that is an invariant. It's an invariant subspace. Invariant subspace of n. All right. So let me go ahead and prove alpha linear independent. So suppose so you're going to go through the proof of that. The proof is actually by induction on the length of the cycle. So if prove alpha is proves linear independent, right? So this is going to be by, the proof is going to be by induction on the length of the cycle, by induction on K. So first of all, if I had K equals to 1, I mean that's the length of the cycle. This has length, okay, there's K vectors in here, right? So if K equals to 1, then alpha is just the set containing X, right? And as we assumed X was not equal to 0, it's linearly independent. Thank you so much. Now what we're going to assume is that n sub, let's say n sub m minus 1 of X. Oh man, that's not the same m. That's not the same, I need a different letter.
R.
R, okay, sure. R minus 1 of X. X is linearly independent for any cycle of length. Any cycle of length, what is it? R. And we need to then consider R plus 1 cycle. We are hoping to show by induction that the R plus 1 cycle is linearly independent, okay? So this alpha is a cycle. It's the cycle with initial vector x. All right. So consider an R plus 1 cycle. So that would look like n R of x. That was x, right? And so suppose, now we'll do what we usually do. I'll use C sub R and compose with itself R full times acting on X, plus CR minus 1 and R minus 1 acting on X, plus plus C1n of X plus C naught X equal to 0. All right? And the thing that makes this, you might be worried like, oh, this is a nasty problem, because I remember the unpleasantness of problem 133 in the homework, which, hey, you didn't post a solution for yet. I did not post a solution for that yet. But I'm thinking about it. I think I know what I need to do. Anyway, I will, of course, soon, but I apparently have 60 number theory problems to do before Friday, so I better get to work on those.
Or you can do it on like Monday. Or like next Monday.
But you have a test on Tuesday.
Well, I mean, that's like if you want to give it to us.
Oh, if I want to give a test,
You don't have to.
I see. It's very magnanimous of you. But the difference here between this and the problem of the homework, and the problem T was just an arbitrary linear transformation, right? This is a much nicer thing. We're looking at a nilpotent transformation, which is really nice because what I can do is I can just, I can operate by n, right? Operating by n, it gives me CR n sub r plus 1 acting on x, right? Plus CR minus 1 n sub r acting on x plus plus C1n squared on x plus C naught n of x, right? Equals to 0. But, I assumed that this was an R plus 1 cycle. What does that mean in our current language?
That it is 0.
Right, that means that I'm assuming that this goes to 0. So look at what we have. We have C R minus 1. Let's see here, n the R minus 1 acting on V, plus plus C1n acting on V, plus C naught V equals to 0, where V equals to what? It's easiest to see from the last one. Nx is phi. But what do we know about the thing that I just wrote in red? This, you see,
So linear combination.
right? It's a linear combination set equal to 0 of not an r+1 cycle,
R cycle.
but of an r cycle. You see nx, if you take nx as an initial vector, where x is an r+1 cycle, if x is the initial vector for an r+1 cycle, then n of x is the initial vector for a r cycle. But we, by induction, know that that's linearly independent. So this implies then that CR minus 1 equal to 0, and so forth all the way down the line, right? And then how do I get that C sub r at 0? Well, I just go back to I can just go back to here, right? So if this is 0 and that's 0 and that's 0, then it follows then, let me just give this thing a label. Call this thing Pac-Man. Okay, so returning to Pac-Man, we get C sub r equal to 0. And hence by induction we're done, because we've just shown that an r+1 cycle is also linearly independent. Okay? So then it follows that the cycle generated by x for a nilpotent mapping is linearly independent, which is nice. It's easier. Showing it's invariant is even easier. Let me show you on the projector now. Yeah.
And whenever you say cycle, you're talking about the number of times you can multiply the matrix before it gets to 0, basically. Because once
Yeah.
you multiply-
For here, a k cycle means that n to the k acting on x is 0. Right.
Yes, but it came out to 1.
And it also, yes, by assumption, and it also corresponds to the length of the cycle, which is the number of vectors in alpha, which, by the way, means that alpha is a basis for Cx, right? And we can also show, now you distract me, all right, so fine, how can we show that n of Cx is a subset of Cx? How would we prove invariance? So what's a typical thing in Cx? So V in Cx means what? V is equal to what? It's what? C naught x plus C1 nx, so forth. Ck minus 1, n to the k minus 1, x, that's it, right? That's the definition of C of x is the span of these things. So if you look at that, if you operate on n, and v is what? It's C naught nx, right? Plus C1 n squared x, plus da da da, plus ck minus 1, well, n to the kx, that's 0, right? So that being 0 means that n acting on x, n acting on v doesn't go outside the set, right? The fact that n to the k is equal to 0 is what enforces the n invariance of this cycle generated by x. So, of course, this is again, n of v is an element of Cx. So therefore, it follows that C of x is an invariant subspace, right? Okay, but so I have this nilpotent mapping, right? I can pick an x not equal to 0 in v, and then I get the cycle generated from x. It may be length 1, it may be length 2, I don't know, whatever. It's some length. Then what's the next step logically? Pick another thing, right? So like, you could say, so if we consider, v, then C of x is some subspace of v, right? And if the length of the cycle of k is less than m, right, then there exists some, let's say, some y, which is not an element of Cx, right? And then you can calculate, you can construct what? You can construct the cycle generated by y. It will have some other length, right? And you just keep doing this until you have enough cycles that you fill out all of v. Right? Now, because it's n invariant, you're going to be able to write v as something like cx, direct sum with cy, and so forth. And because these, we have the basis, and I showed you last time, well, I can't write all this stuff out. I have to use the projector, guys. There's too much to write here. Uh-oh. Hurry, Sharon. Hurry.
I don't got it.
Hurry. Sorry. Oh, okay, it's ignoring me. I'm sorry, guys. I'm going into too much detail here. I need to stop. What? All right. So remember last time we saw what the matrix of n restricted to this x cycle looked like, right? We argued last time that this was what it looked like for the n. If you take n, you restrict it to the x cycle, then you get this matrix with zeros in the diagonals and 1 on the super diagonals, right? So it's a k by k block. There will be k minus 1 copies of 1 on the super diagonal. All right, and this is the canonical block corresponding to the cycle, right? And what I'm saying is you can keep finding these cycles for n until you have enough to fill out the whole space V on which this nilpotent maximum is acting. All right, so I don't want to go back through that again. We did it last time, right? So here's the thing. Here's the proposition. If I let alpha sub I be the ith cycle, all right. So the ith cycle has initial vector x sub I. So like x sub 1 was my x in what I just covered up. X sub 2 would be the y in what I was just writing. And you keep going. So you've got x1, you've got x2, you've got x3. However many cycles, however many initial vectors you need in order to fill out all of v. And so the set of, and what are eigenvectors? Well, like I was telling you, the start of the cycle is an eigenvector, right? You have one eigenvector for each one of these cycles. Actually, everything beyond the first thing is actually generalized eigenvectors of order 2, 3, 4, all the way up to k. This one is a kth. It's a generalized eigenvector of order k, because n to the k acting on x is 0. Okay? But anyway, so you have these cycles, and I'm just supposing I have r of them. So the claim is that alpha 1 union alpha 2 union alpha r is linearly independent. So how would you prove that that union of cycles is linearly independent? What you do is you do the same thing we always do. Suppose you have a linear combination of all of them equal to 0. So I need to show the coefficients in that linear combination of all these different vectors is 0. And that's where this beautiful tableau picture comes into play. Let me show you how it works. So what we're going to do is we're going to use a picture. It's called the cycle tableau. What was the question you played with?
I was going to ask if, like, say you had alpha 1 up there, and you took a span of that, would that span be?
Would that what?
If you had, like, set alpha 1 with all those nilpotent thing, the cycles, if you took a span of alpha 1, would that span be?
No.
It wouldn't. But if you took the span of the union of all them things, would the span be?
That's what we're saying, right? Okay. Now I want to. Now we know that each cycle in and of itself is linearly independent. But the question is, do the cycles overlap? I'm now going to give you an argument by this tableau argument, this method of tableau, that if you have a simple condition on the eigenvectors, it turns out if the eigenvectors, these guys, in all the R cycles, those form a linearly independent set. If you have linear independence of the eigenvectors, okay, in each cycle, then that implies linear independence of the cycles as a whole. So here's how. So here's the picture. Without loss of generality, we can assume we can reorder the cycles so that the first one's the longest. Okay, so suppose your first cycle for this is, so for my picture, my example, suppose that the CX1 had length 8. Suppose CX2 had length 4, CX3 had length 4, and so forth. I mean, this would be a picture of what's called the cycle tableau. So you have to imagine in your mind taking a linear combination of all of these vectors. So in this case, in my picture, my total dimension for V would actually be 8 plus 4 is 12, 16, 18, 20, 21, 22. 23? Okay. So this picture, here's the way it works. This corresponds to the first thing in the cycle. These boxes represent the eigenvectors, one from each cycle. All right? And this is the initial vector for the first cycle, initial vector for the second cycle, initial vector for the third cycle, initial vector, initial vector, initial vector, initial vector, initial vector, for each of these cycles. So, and the way it works is if I operate by n, it basically pushes the diagram over. All right. So if I take this initial vector and I operate on it by how many times? 7 times. What happens? This diagram gets pushed. This gets pushed off to the everything here as you operate by n goes to 0, 0, 0. So if you take that linear combination and you operate by n 7-fold times, all that's left is this box. And so then you can conclude that the coefficient of that initial vector is 0. Right? But if I operate by 6 times, I get the coefficient of this one is 0. If I operate by 5 times, this one is 0. 4 times, this one is 0. If I operate 3 times, that pushes this over to here, where then those are eigenvectors. The images go to the eigenvectors, but the coefficients would be the same as you had initially. Everything else has gone to 0. You already know that everything else over here is 0, so you don't worry about that anymore. And so then you can show these are coefficients are 0. And then operating 2 times takes this over here. Again, you can argue that 0 because after you operate by 2 times, you're down to the eigenvectors, which you were assuming linear dependence of. And you just repeat this until finally you have all of the coefficients are 0 by this argument. It's just successive operations of n to push things to be the eigenvectors, which we're assuming are linear independent. So it's very sneaky. If I had to actually write that down, it would take me a whole class, and I would have to invent notation. And after I invented the notation to show you it, none of you would understand. Yeah.
When you say coefficient, you're talking about that equation you had up on the board, and like the C's are the coefficients.
I didn't write the coefficients, that's my point.
So these are imaginary coefficients?
These are in our mind coefficients. I'm saying take all of the cycles together. You have a set of 23 vectors,
Yeah.
right?
Yeah.
So one of those vectors, let's say that's V1.
That's yes, the initial.
So you have C1, V1, right? Plus C2, V2, plus all the way on out.
Yeah.
If you operate by n 7 times,
Yeah.
everything is gone.
Because it's like it's 0, it goes to 0.
Right, because everything else, if you hit it with a power of n less than 7, goes to 0. All you'd be left with would be C1 n to the 7th times V1. But n to the 7th times V1, because this is an 8 cycle, is an eigenvector, which is by definition non-zero. Consequently, I get that C1 is 0.
Okay.
Plus C2, V2. Well, same argument. Operating the 6th power, I'm just left with like C2 times n to the 6th V2, the V2, plus n to the 6th V1. The V1 is still there, but you know what? I already know that C1 is 0, so we don't care about that. You're just left with n2 times n to the 6th times V2,
Yeah.
which by definition
The coefficient must be
is 0.
That makes sense.
Okay, so that's the argument. I mean, it's.
When you
and-
say it goes on out, like does it go to infinity or does it go to 23?
Well, I picked an example of 23 to try to, rather than trying to do it for an arbitrary number, because I think it's helpful. The book, I think, has some other examples, but I thought this was weird enough that it should get the idea across. So maybe we go on. This really isn't the big point here. Anyway, so again, just to recap, the idea of the picture is eigenvectors in the leftmost column operating by n pushes the diagram to the left. And anyway, so that gives us linear independence, and consequently, that makes, when you string all these alpha 1 through alpha r together, then you have the canonical form for a nilpotent matrix, which has this form. It's basically blocks with zeros on the diagonal and then ones on the super diagonal, right? Every one cycle you have, you just get a 0 with no 1 above it. So the number of zeros at the end of this, because we're just listing them in order of increasing size, the number of zeros at the end corresponds to the number of eigenvectors, actually. Oh, excuse me, the number of just eigenvectors sitting off alone in their own cycle. Actually, to get the total number of eigenvectors, what you'd have to do would be to add every time the first thing in each block that corresponds to an eigenvector. All right, so there would be R eigenvectors, actually. There's KR cycles, there's one eigenvector in each cycle. Okay, so the number of blocks corresponds to the number of eigenvectors. Yes, Landon?
Basically, yeah, because on each, what you just said, each alpha has one unique eigenvector.
Right.
Okay.
Now, there's also a technical result, which the proof is like, it's a beautiful proof. I'm not going to spend time on it here. We're out of time, so you can read it. It's some kind of, there's like some sort of telescoping rank nullity argument. It's very interesting. But it turns out the number of boxes in the jth column, all right, what that means for the nilpotent matrix, it's the dimension of the kernel of nj minus the dimension of the kernel of the n to the j minus 1th power. Take, for example, j equals to 1. J equals to 1, j minus 1 is 0. What's n to the 0 power? It's defined to be the identity. What's the kernel of the identity matrix? Solve ix equal to 0. You get x equal to 0. So the kernel of the identity is just 0. So in the case that we have j equals to 0, j equal to 1, this just becomes the kernel of n. And by the way, the dimension of the kernel of n is the number of eigenvectors, right? That's the eigenspace of 0, which then is the number of boxes in the leftmost column, which is what I was just saying before. So this result goes back to the tableau and the example I think. But more than this, the number of boxes in each column reveals to you the difference in dimension of the power of n, one power separated. That's just really very, very insightful, this little lemma. And so what that means then is that the canonical form of a nilpotent mapping is unique if we arrange the k-cycles in increasing order. Now, I know you guys want to see some examples, right? So here's some examples. So for example, if I know that the kernel of n was 2, which means there's 2 eigenvectors, and if the kernel of n squared was 3, that actually means that there's 3 generalized eigenvectors of order 2. Language. He never defines generalized eigenvector of order blah. I said generalized eigenvector of order blah means that the operation to the blah minus 1 is non-zero, but the operation to the blah is 0 on the vector. So like that was our definition. I think it's still valid, but he would say this. He would say that there are 3 generalized eigenvectors in this space. There are 4 generalized eigenvectors in this space. Actually, I don't know, you might insist on this being the only thing. Please stop. Shut up. So 3 minus 2 is 1, right? So that means the third column has 1 box. 4 minus 3, 1. But then what's the other one? Oh, I think I'm doing it wrong. Sorry. J minus, so excuse me, n minus 0 is 2, that's why there's 2 boxes here. 3 minus 2 is 1, that's the 1 box. 4 minus 3 is the 1 box. Here's another more complicated example. I will post these, obviously. Okay, so the kernel of n being 10, that means there's 10 eigenvectors with eigenvalue 0 for n, right? So that would give you 10 boxes in this tableau like that. And then if the kernel of n squared was 16, that would mean that when you look at n squared, you get 6 more linearly independent vectors in the basis for that. Of course, you also have all the eigenvectors in the kernel of n squared. They're still there, right? But you get 6 new things is the point. So that's why 16. So 16 minus 10 gives you 6. That's really, I would say the number of generalized eigenvectors of order 2 is 6 here. Generalized eigenvectors order 3, I would say, is 2. Generalized eigenvectors order or 1. There's just one generalized eigenvector of order 5. Okay. That forms the initial vector for the 5 cycle here. And so you can piece it together, and then you can see how many different cycles you have. Of course, you know there are 10 cycles from the 10 eigenvectors, right? But you can also see the length of each cycle as you look at the tableau. There's a 5 cycle, there's a 3 cycle, there's 4 2 cycles, and then there's these 1 cycles down here. These correspond to a 5 by 5 block in the matrix. This is a 3 by 3 block. This gives you a 2 by 2 block, 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 and then zeros, which I had written over here. Yes?
So basically, with these, like you have all the initial eigenvectors, and then multiplying by n on the left, for some of them won't give you anything new. Some of them will, like eventually will end up being 0, and that's where you get those tableau boxes wrong.
Right. Operating by n on these just makes them go to 0 because they're
Yeah,
eigenvectors.
exactly.
But operating n on this brings you to that, okay, and so forth. Now, we're not really that interested, I mean, guys, by the way, we're not really interested in nilpotent maps, right? This is actually just a way station on to a place we're really interested in, which is the Jordan form. So, the Jordan canonical form, the center of the construction is based on what's called the generalized eigenspace. And so, you look at the characteristic polynomial, all right? So notation, the characteristic polynomial for a linear transformation T. So let's let T go from B to B. And we're letting P of T be the characteristic polynomial. Usually that's the determinant of T minus Ti. And what happens, we can write it this way. This is equal to lambda 1 minus T to the m1 power. And then lambda 2 minus T to the m2 power. Lambda, what did I use, K? K, yeah, lambda K minus T to the mk power. Now we're assuming that m1 plus m2 plus plus mk is equal to the dimension of V. In other words, we're still making the assumption we made in section 6.1 that you have as many roots as you need to fill out all of V. I mean, there's as many roots to the characteristic polynomial as there is dimension in space. This is automatically true if we're in the complexes, right? Which, anyway. So, and these are the so-called algebraic multiplicities, right? Algebraic multiplicity of what?
The
Lambda
Of lambda 1, right, yeah. And I am assuming that lambda 1 is not equal to lambda 2, and so forth, right? Lambda I is not equal to lambda j, for I not equal to j, okay? So, here's the thing. For any eigenvalue, lambda I, we can construct the generalized eigenspace, k sub I, to be the kernel of t minus lambda I to the m sub I power, m upper I power, m sub I exponent. Now, the critical result, which is proved in section 6.3, is in fact the dimension of the generalized eigenspace is mi. So these have full dimension. They have enough vectors in the generalized eigenspace to pick up the m sub I, which appears in the characteristic polynomial. So what that means is if you think about k1, k2, all the way out through k sub k, you've got enough vectors in those, and a basis for those, if you string them together, that you get a basis for V. That basis is called the Jordan basis. And so let me show you. That's the technical result, which is not an easy thing to prove. It would really take me about 2 careful days to really prove that, honestly. Proposition 6.3.1, it's got a double induction or something. It's, I don't know, I had to think about it some. But it's not, it is constructive. He actually motivates the construction of these generalized eigenspaces by finding an invariant subspace and like, not finding an eigenspace and just like sort of adding vectors to it in such a way and proving that that space is invariant. And he doesn't just generalize, he really does motivate this definition of k sub I in this section if you read it carefully. I probably haven't. Okay, so if you look at define n sub I to be t minus lambda I restricted to the kth generalized eigenspace. This is m sub I dimensional. That means that if you take this n sub I and you raise it to the m sub I power, you have a nilpotent map.
So this is 0.
Right, so this is 0. But that means that we can construct the canonical nilpotent basis for the ith generalized eigenspace, k sub I. In other words, there's a basis beta sub I such that the matrix of n sub I looks like this. But it's also equal to t minus that. So you also have the matrix of t with respect to the ith basis, the basis for the subspace. And then this diagonal, right? So when you take this matrix and you add it to that one, that gets you the ith Jordan block for t, which simply looks like this. So it's lambda sub i's down the diagonal. This is the eigenvalue of the corresponding to the ith generalized eigenspace. And then ones on the super diagonal as needed, according to the nilpotent cycles we were talking about. Yes?
So I see what you're doing. Just where did the nilpotent thing come from again? The
Nilpotent thing comes from restricting t
Yeah.
to the jth generalized eigenspace.
Okay.
And so, if I have lambda sub j minus t to the m sub j power, I can argue that if I restrict to that, it has to be 0.
Okay.
But so that brings us to the Jordan form, which states simply, if you have a vector space with enough roots over f, you can always find a basis that makes the matrix block diagonal, where the blocks are Jordan blocks, which is just the eigenvalues down the diagonal, and either ones or zeros above, according to the particular nilpotents that you encounter with t minus lambda. I'll be more specific in the examples that follow, but that's the Jordan form. It's almost diagonal. It's eigenvalues down the diagonal, and sometimes and ones above as needed. If there are any ones above, that means your matrix is not diagonalizable. Yeah.
And this is for any linear transformation.
Provided our field is algebraically closed. If we're rotations, for example, can't be brought into Jordan form using just real technology. I need to complexify. If I complexify, then I'm good because complex numbers are algebraically closed. Every polynomial factors, and so into linear factors.
Okay. So if you had like a lambda value of 0, then you would have to use a complex space.
0 is fine. If I have lambda of I, complex, like 1 plus or minus I, 2 plus I. Oh, here's an example. So, and again, I'm just going through the argument again, which was that the kernel is m sub j dimensional. So if I take the restriction to that m sub j dimensional space, if I raise it to the m sub j power, that has to give me this nilpotent map and so forth. But we just went through this. Let me go on. I want to show you an example or two, right? Here's an example. This A is in Jordan form. All right, so finally, we have 8 minutes to do the part that I'm more likely to test you on. Sorry. So we still have to cover section 6.5. We're not quite done yet. Anyway, so if this was the Jordan form, I can read from this certain things. For example, the eigenvalues. The eigenvalue of A, it's very boring, it's just 1, 1, 1, 1, 1, 1. Right? This is an upper triangular matrix. The eigenvalues are in the diagonal. Right? Don't forget that, it's always true.
It's not diagonalizable, is it?
It is not diagonalizable, right? Because it has that super diagonal, right? So there's the ones there. That means if you were to restrict, if you were to think about the linear transformation corresponding to A, like L sub A restricted to the generalized eigenspace corresponding to those three, E1, E2, E3, well, A minus I restricted to K1 would be nilpotent order 3. A minus I, the third power, restricted to the span of E1, E2, E3 would just be nilpotent order 3. I know that from this. more to the point here, the characteristic polynomial would be 1 minus t to the 7th. All right. How many eigenvectors are there? 1, 2, 3. How many generalized eigenvectors are there that are not eigenvectors? 1, 2, 3.
Wait, would it be 4?
Oh, I'm sorry, 4. Did I say 3? There's 4 eigenvectors. 1, 2. Look at this. This is diagonal. Notice the 1 here. So really, I should do that if my picture was better. Sorry. So here's another example. I have a 4 chain, I would call it, with eigenvalue I. All right. Then here's a lonesome eigenvalue I just sitting there. Here's 3 eigenvalue 3s. They're forming a chain. You've only got 1 eigenvector with eigenvalue 3. This corresponds to having an eigenvector, generalized eigenvector order 2, eigenvalue 3. Generalized eigenvector order 3, value 3. And then I've got 2 eigenvectors with eigenvalue 2. And just to be a little bit, to bring it back to what we were doing earlier today, for this matrix, which I'm just talking about, the characteristic polynomial would be I minus t to the 5th times 3 minus t to the cubed and 2 minus t squared. The dimension of E1 is 2, the dimension of E2 is 1, the dimension of E3 is 1. If you look at A minus I, you have this tableau. I had 2 eigenvectors, and I had 1 4 cycle. So the tableau for this nilpotent map would be that. The tableau for this nilpotent map, A minus 3i restricted to K2, would be that, because it's just a 3 cycle. Boring, but there it is. And then the tableau for, because we had 2 eigenvectors with eigenvalue 2, that was it. A minus 2i restricted to K3. K3 in particular would be the span of the last 2 standard basis elements for here, would be that tableau. So if you think about these tableaus, they really unlock how to think about all of these things together, let's say. Now, there's some really wonderful things you can say about the Jordan form. I want to use the Jordan form to prove a couple simple things for you. The one, any matrix A over an algebraically, let's say algebraically closed field, you can write it as the sum of a diagonal and nilpotent. That should be obvious to you from what we did today. What's the diagonal?
Diagonalized.
I mean, A is equal to, the eigenvalues, lambda 1, all the way out, whatever. And then you've got plus that matrix, which is 0 is the diagonal, and then epsilon 1, epsilon n minus 1, where these epsilon 1, epsilon n minus 1 are just equal to 0 or 1. The point is that this is a strictly upper triangular matrix, right? This is diagonal. As you can see, A is equal to D plus F. Oh, I'm sorry, but I don't know that A is in Jordan form, do I? So what do I need to say? If A was already in Jordan form, we'd be done, right? But we don't know if A is in Jordan form, do we? So what should I do? Really?
Wait, how is A not, if like you have in all the...
Well, the A I wrote is in Jordan form, right? But what I really should say is that P inverse P is equal to this, right? So that would be the Jordan form corresponding to A, let's say. Now that, J sub A is equal to D plus N. So we've got P inverse AP is equal to D plus N, right? Now how do I solve for N? P D plus N multiplied, sandwiched by P and P inverse, right? If you take a diagonal matrix and you sandwich it, if you do similarity transformation for a diagonal matrix, what do you get again? You get PDP inverse, which is not necessarily the same matrix, but it's again a diagonal matrix. I'll let you prove that. Sharon asked me some question the other day which made me believe that. So this you can argue is diagonal, right? That's a lot easier than doing it. I mean, it's not that hard to prove that's diagonal. And this being nilpotent, well, that's even easier. If I call this thing n tilde, right? And I raise n tilde to the, let's say, n power, I'll get p n p inverse, p n p inverse, p n p inverse n full times, right? And you see the p's cancel, and you get n to the n, p inverse, right? But by construction, this is an upper triangular matrix, and by n strictly upper triangular matrix, and it's easy to prove that that's 0. So as you can see, the matrix similar to, in other words, a matrix which is similar to a nilpotent matrix is also nilpotent. So diagonal, what's the word? Diagonal, how do you call that? I don't want to say diagonalizability, I want to say diagonality. Yeah, maybe diagonality is preserved under similarity transformation. And nilpotence is preserved under similarity transformation. Yeah. Yes. Yeah.
I was wondering, how do we define P in there? How do we find P and be able to figure out what it is?
Jordan form.
Wait, I thought we're multiplying P inverse plus P gives you A, which is the Jordan form.
I mean, how do I find D and N? These are the Jordan form for A.
Well,
How do you find the Jordan form for A? That's a rather complicated question.
Yeah.
That's answered in section 6.4. It's involved. Basically, you gotta, first of all, find the characteristic polynomial, identify your eigenvalues, and then find the length of, and then you have to start investigating t minus lambda powers and find the highest one, which is non-trivial. That will find you an initial vector for the first chain, and you just keep building chains. There's lots and lots of examples in the book, but it's rather complicated. I'm more interested in understanding the structure of a given Jordan form as opposed to actually calculating one. There are 3 homework problems which are based on constructing one. Okay, so the other thing I want you to see is it is trivial to see why the trace of a matrix is the sum of the eigenvalues, and why the determinant of a matrix is the product of the eigenvalues, given the Jordan form. These are also easy to prove if the matrix is diagonalizable, right? But how do you know the trace is the sum of the eigenvalues? Use the Jordan form, right? Jordan form is similar to A. The trace is invariant under a similarity transformation. We proved this before. The determinant is invariant under similarity transformation. So whatever the trace of the Jordan form is, and whatever the trace of the whatever the determinant of the Jordan form is corresponding to A, those are the trace and determinant of A, respectively. So it's obvious that the trace of the Jordan form is the sum of the eigenvalues. It's obvious that the determinant of the Jordan form is the product of the eigenvalues. Consequently, the same is true for A. Yeah.
Is that because of when you write it out in the Jordan form, and then if you were to add them together, if just the diagonal would be them?
Yeah, the determinant and the trace is the sum of that diagonal. So that would be much more difficult to prove without Jordan form. Anyway, I will tell you about the minimal polynomial. It turns out I can tell you what the minimal polynomial is from just looking at the Jordan form. What is the minimal polynomial? You know that P of t is equal to 0, right? So the minimal polynomial is the smaller possible polynomial where g of t is equal to 0. So it's a smaller polynomial possibly, which also makes the corresponding linear transformation go to 0. So it could be the characteristic polynomial, but it's not usually. It's usually something smaller. And you can figure out what it is by just looking at the blocks in the Jordan form. It's really simple. So we'll do that next time and then answer any questions you might have. Thanks, guys. When is the homework due?
Friday.